for the purpose of our analysis and they're not included, right? So that is listwise deletion. Multiple imputation is our third option. So in this case, we look and say, we have one person missing. What are we going to do? Well, we're just going to scan around in the stadium and pick the person that we think is most likely like the athlete that is missing. So in this case, we're like, okay, this kid looks like an athlete. He's wearing clothes of an athlete. So let's just grab him and let's have him standing for the guy who is missing. That's what we do here with multiple imputation. The word multiple implies that we do that several times, right? We're trying to guess multiple times so that we can average them out and see who is the best candidate to replace this guy that is missing. But bottom line, that is a mental image we want to create, that we scan around and say, okay, this guy looks the closest to what we think. Obviously, we don't know who is missing, but we're saying what we think this guy is most likely the closest person. So let him come and stand in for the missing guy. Then scenario number 4 says, well, the one guy is missing, but how about we take this, the fourth athlete who was here, and we make him much bigger, right? Like we'll make him really big so that his size represents 2 people. So even though he's 1, well, he has now been inflated. So he has the size of, like 2 people. So it's like this is a sumo wrestler on steroids, maybe literally on steroids. All right. So that is what we're trying to achieve. So this forms a framework of how we could possibly handle missing values. We could do nothing. We could do listwise deletion, where the guys who are missing remain missing. We keep them as missing. That means that they're discarded from the analysis, so that our fight involves only one regular guy. No, he's not extra large. He doesn't have somebody else replacing him. He's just alone in the fight. Option 3, we look around the stadium and say, we will pick the guy who we think is closest to the guy who is missing, so that we have 2 people here. So the first option, we have 2 people in the rows, and here we also have 2 people. And then lastly, we say we're going to supercharge this guy, so he's really big, and so he's like 2 guys in one. So it's still 1 person here, but it's like 2 guys. Those are the 4 possible options that we have, broad options we have. So we are going to look at each of these options and think of when it makes sense and what the consequences are. And so for the rest of the lecture, I'm not going to focus too much on technical proofs or how to write code. We're just going to focus on intuitive understanding of what's happening. It doesn't help you if you know how to write the code, but you don't understand what's happening, right? So we're going to focus on high level, what is happening behind the scenes, and as scientists, how should we think about those processes, right? Later on, I dropped a homework on LinkedIn. So I'm going to share the code with you later in our community, so that you can at least look at how the code is structured and how that works. But for now, for the lecture, I'm not interested in code. I'm just interested in how do we all understand intuitively what's happening behind the scenes. So that's the framework. Now, the most important thing we want to care about when we're evaluating decisions about missingness are 2 things. We care about validity and we care about precision. So those are 2 things we want to understand. Now, for the sake of our illustration, here are the rules. Validity is when this is the note these guys wrote after their fight, right? If what they wrote is correct, then it's valid. And if what they wrote is legible, we can see it very clearly, it's sharp, then it's precise. So that's very simple. So validity is if it is true, and precision is if it's legible, if it's clear, if it's sharp, right? So that's the rule we're going to set up. And so we're, again, keep it very simple. The goal is we want to understand intuitively what is happening and the consequences when we decide to take one approach over another. All right, so first scenario here, these guys won the first place. And this is the note they wrote. They said, we crushed it together. 2 big boys, full strength. So my question is this valid? Right? And somebody can, someone can raise their hand and answer the question. Is it, again, 2 questions we're asking, right? Is it valid? And is it precise? Remember the rules. Validity is if the information they wrote to send to their friends back home is actually accurate. And precision is if it's legible, right? And so want somebody to answer the question.
You can raise your hand. Someone in the chat said valid and precise.
Okay. I want somebody to explain to us why it's valid and precise.
Can you raise your hand so I can unmute you, Peter? Okay, you can unmute now.
Okay, good evening, Prof.
Hello.
Thank you for, So the game is for two people of equal sizes. There are two people here and the sizes are equal in all respect. So I think it's valid to the point that the game is for two people and they're precise because the two people have equal muzzle or weight value.
All right, thank you. Thank you very much. But thank you for that. But we're evaluating validity and precision based on their message. This is the note they sent back home. That is a framework with which we're evaluating validity and precision. So can somebody else give us their own perspective based on the note they wrote home here? Is it valid? Is it precise?
Harrison?
Yes, from the explanation from Prof. The answer is here. It is valid because they say we crush it together. I won. So it's valid. And precision is clear. I can see it clearly. If two big boys, full strength, did it together, they won. They crash it together. So it's precise.
Thank you. Now, while I still have you on the line, after such a long fight, why do you think their handwriting is still so sharp and legible, as opposed to being weak and illegible? Why do you think that is?
That is the precision we are talking about. When it is clear and we can see it,
okay,
that they have the strength, full strength.
Okay.
They can even fight again.
Excellent, right? So the point I'm trying to drive here is that the handwriting is clear because there are two of them. Like you said, they can still fight again because, well, there are two big guys who were fighting, and so they still have some energy from them in them, and that's why they can still afford to write very legibly. So the point is that precision is driven by the number of people we have. Obviously, if you had four of them, it will even be much more sharper or even much more precise, right? Precision is driven by sample size, as opposed to if you had just one guy fighting against this two guys, he might win, but at the end of the day, he might be so weak that the handwriting will be very, very legible because he has no energy in him. So the point is, we are assessing validity based on the truthfulness of the statement, but in this context, we're assessing precision based on, how is it clear, is it sharp? So what we want to remember from the illustration is that when you have a complete data set that doesn't have missing data, it might be valid. Of course, this is assuming that it is randomly selected, right? And it's precise because you have a full data set, and so the larger the numbers you have, the more precise it's going to be. So yes, the message is true, so that means it's valid, and the text is sharp, which means it's precise. Now, just to also make it very clear that when we talk about validity, there are two aspects of it. There is validity that happens inside the ring and validity that happens in the streets, right? Now, why is that distinction very important? Who cares to share? Why do we want to make sure that we make a clear distinction between what happens in the ring versus what happens in the streets?
Alison,
Does that have to do with external validity and or ecological validity that in a controlled setting is not necessarily representative of like real world settings?
That's very correct. Yes. So we want to make sure we are very, very aligned with that, because the fact that they won in the ring does not necessarily mean they will win in the streets, because the streets and the ring are quite different things. So when we say that there is validity with this full data set, the fact that you have a full data set, there may be validity within your data set, but that doesn't mean that your results are generalizable to the streets, because the streets and the ring are quite different environments. So we want to keep that in mind.
Something was wrong. A sick, twisted
please keep it up.
discovery. We found child pornography in water.
All right, thank you. So the condition for generalizability is that there has to be random selection. Again, this is the cycle of inference. From a population, we get a sample through the process of sampling. And the sample, if selected at random, gives us inferences which we can draw back to the population. And this is what we refer to as a cycle of inference. So the moral of the story here is that the fact that your data set is complete and there's no missing value, that in of itself does not guarantee that you have generalizability. Generalizability is guaranteed only and only if the selection of a sample from the population was done at random. So we want to keep that in mind. All right, here is team number 2. Again, remember, this is the one guy who fought, right? And he had no second person to help him, which means listwise deletion. Listwise deletion is the data are missing and we keep them as missing, which means that in your analysis, they are thrown out of the picture. So it's only the one guy that is remaining. It's only him that has to fight. Now, this is his message after the fight. You know, he clearly got the last position. Now, who can tell us, is his message valid? And is his message precise? And why do you think it is that way?
again, you can raise your hand if you want to speak. Someone says his message is not precise. Rosemary, would you want to speak? Okay, Abdul.
Hello, Professor. I think his message is valid, but it is not precise. Why it is valid? Because the message is true. But it's not precise because it is not readable enough. It is not visible enough. Because he fight on his own and he was alone, and so that's why I think the data was not precise enough. But the data was true in itself. I think that's my thing.
You're absolutely correct. I mean, try fighting 2 giant fighters and let's see how you will feel at the end, right? And so that's his experience. He's super, super tired, and so he can barely write. And so that should help you remember that precision is always driven by numbers. If you're just one guy fighting, you know, a battle, of course, you're going to be tired. You won't have precision. And so in this case, he's valid, but he's not precise. So what does that mean? How does that apply to your data set? When you do listwise deletion, assuming that there is basis for doing listwise deletion, the results may still be valid, but you will have loss of precision because you have a smaller sample size. The smaller sample size will always result in less precision because precision is driven primarily by numbers. If you have more people, you're going to be more precise. If you have less people, you're going to be less precise. So it's pretty straightforward. So in this case, like we have established, the message is true. Yes, he lost. He was very honest, so that's valid. But the text isn't sharp. So there's lack of precision. And why? Because he's just one guy. That's why he has diminished precision. Now, we need to understand why that happens. In the case of, again, we said earlier that the fact that you have listwise deletion doesn't necessarily mean that it's valid automatically. And we need to understand the scientific basis of that statement. So here is what happens when people leave your study. So people enter and people leave. This act of leaving is what we call as missing values, because of course it's still in your data set, but it is not actually there. It's just the ghost of itself. The act of missingness means that the individuals who have missing values have left the analysis. So the question is there a systematic difference between individuals who have left and those who are remaining? That is the crux of the issue. If there is a systematic difference between those who left and those who stayed, then obviously that means that the individuals who have remained are no longer generalizable to those who have left or to the general population overall. So once there's a systematic difference, right, that means then that it is not valid, so we want to keep that in mind. So when we say that this message is true, we are assuming that there is no systematic difference between those who left and those who stayed. In other words, those who had missing values did not differ systematically from those without missing values. So that's a very key assumption we want to keep in mind. Now, when you do listwise deletion in your analysis, remember we've established from the previous weeks that the core assumption of listwise deletion is MCAR, that the data are missing completely at random. So in other words, there is no significant difference between those who left and those who did not leave. We can say that statement in so many ways. When we say that it assumes MCAR, one way of saying it is that those guys who left are non-differential from those who did not leave. That also, another way of saying it is to say that those who are remaining in the survey are representative or do not differ systematically from those outside, right? And many ways, but the idea is that there is no association between leaving the study and any factor. So it's not as if something triggered you to leave. So if something triggered you to leave, that means that there's something related to you leaving. But MCAR here indicates that people just left for very, very random reasons. So that's the assumption that is in place when you analyze data with listwise deletion, right? So we need to really, really understand that. At the end of the lecture, we're going to look at a framework to make decisions. But for now, we just want to understand, at least intuitively, what is going on and what the assumptions are when certain analyses are done. So in this image, for example, where our analyzed data sets, the individuals who remain, we are assuming that they are completely exchangeable with the entire original data set, and that is exchangeable with the original population from which we sampled. If any of these assumptions are wrong, then you have no business doing listwise deletion, right? Because the underlying assumption for listwise deletion is MCAR, missing completely at random. All right. So here's team number 3. This is the multiple imputation. Remember, this is the scenario where we just randomly grabbed some guy in the audience and said, hey, come and stand in for this guy who is missing, right? Because we think that you are a perfect match for him. All right, so this is the statement. Now, can somebody tell us, is it precise? Is it valid? Remember, they took the last position. But here is what they wrote home. Is it valid? Is it precise?
So I think that data is not valid, but it is precise. Precise depends on the sample size. So we are filling numbers. That's why it is not valid. But because the number is fulfilled, there are 2 of them.
Okay, thank you. We're really struggling to hear you. The line was breaking. Just so all of us on the same page, can someone else just maybe re-echo or provide their own opinion on this?
Hello, sir. Yeah, so I would say it is precise, but it might not be valid because this second guy, the carrot guy, may not necessarily represent the population of the giants that we saw at the initial. However, the fact that there are two people here, it's that increases the number of size and the sample size, and it's likely to be it is precise, or it will be more precise than one person being here. But for validity, it's not valid.
Excellent. Agreed. So it's not valid, but it's precise. And again, remember, precision is driven by numbers. As long as you have people, your results will always be precise. That does not mean it's valid. So we want to keep that in mind. Very important. So our problem started with the assumption that because this guy looked like an athlete, then he was exchangeable with a sumo wrestler. So in other words, what we have effectively done is misclassification. We have misclassified this guy here for a sumo wrestler. We just assume that, well, they look alike. They're all wearing sports attire. They're all males. And so, well, we can interchange them. This is what is happening when you do multiple imputation. It's a guesswork, right? Because you don't even know the original value. So you're playing a game of guesswork here, like, I think that this guy will be a perfect match based on what I think the guy would have looked like. And that is the danger with multiple imputation. There are three main types of biases in epidemiology. We have confounding bias, selection bias, and measurement bias. Of these three, the one that receives the least love, but is the most deadly, is measurement bias. I call him the bastard child of epidemiology because nobody talks about measurement bias, right? We talk about confounding and all of that, but the bias that you actually need to be worried about all the time is measurement bias, because like I said, for the other biases, you can have medicine after death. For confounding and selection bias, we have statistical methods we can correct for them post facto. Measurement bias, once it's done well, you are really, really screwed, right? And so in the case of multiple imputation, that is the biggest thing we have to worry about. The issue of misclassification, which is an example of measurement bias. Like I said, three types of biases in epidemiology. If it's confounding, you can correct it, right? Confounding is a thief. We call it a nuisance variable. There are many ways we can correct for it. Imagine in this illustration here where you have farmers who come to the grain, to the granary to store their grain, and the confounder just comes, steals the grain, and walks away. So what confounders do is that they steal explanatory power between the variables in question. So let's say we're looking at the relationship between bringing your grain to the granary and the amount of grain in the granary. Those are the two things, right? You expect that as we bring more, well, we're going to see more. What confounding does is that it comes and steals the grain so that you're like, this doesn't add up. We have X amount of grain brought in, but Y amount of grain here. What is happening? Well, what's happening is that there's a thief here. Confounding. Confounding is stealing that relationship. That's what happens in any relationship we're capturing. If we're looking at the relationship between, let's say, physical activity and, let's say, mortality, well, there may be something that is stealing the relationship or explanatory power between those two variables. And in the case of confounding, there are things we can do about it. Like, think of this literal example. We can secure the doors. We can bring in, can we please stop writing on the screen? Thank you. We can close the doors of the barn. We can bring in some extra military guys or some guards to protect the barn. There are many, many things we can do to stop this thief from breaking in and stealing grain. So with confounding, we have a whole bunch of tools. In fact, if somebody looked at epidemiology, they might be forgiven for thinking that epidemiology is all about confounding, because as epidemiologists, we surely do talk a lot about confounding. So of the three keys that epidemiology has, confounding, measurement bias, and selection bias, confounding is the easiest to deal with. The same thing with selection bias, right? We can diagnose selection bias quite easily, and we can also correct for selection bias quite easily. let's say you do a national survey and you have your final participants and you realize that, geez, these individuals do not match with what we have in the census. So let's say in your census, you find that 50% of the population is men and 50% is female. But in your survey, 75% are men and 25% are females. See, right now we have already diagnosed that there is selection bias. And how did you do that? Well, we compared the distribution in our study with that in the census. That's easy. And we can now that we have diagnosed the problem, we can easily solve it. We can use calibration weights. And this is standard procedure. This is what we do in large national surveys. We use weights to correct this problem. So again, with selection bias, even after death, we have medicine after death. We can correct the problems after they arise. Same thing with confounding. Well, with measurement bias, it's not so easy. It's not so straightforward, right? Once we have misclassified, well, we are really, really screwed at that point because there's not much we can do. We just have to go home with a fake result. And so that's the biggest threat when you have to worry about, or when you want to do multiple imputation. The threat of misclassification should always be over your head, and you should worry about the issues, because the fear is not that there will be misclassification. The fear is that we don't know the direction that will take us, because misclassification can bias results in any direction. You can never know, right? There are two types of misclassification we have to worry about. One is differential misclassification. The other is non-differential misclassification, right? I will quickly explain the two so that we can see why this is such a problem for us. Differential misclassification, as the name implies, differential means different. So you have two sides. It means that the misclassification is different in one side versus the other side. So let's say we're trying to compare an orange to an apple. But for whatever reason, we misclassify the orange as an apple. Now, suddenly, instead of comparing an orange to an apple, we are now effectively comparing an apple to an apple. So what do we conclude? We say, oh, there's no difference between the two of them. That is false similarity. Now you're biased towards null because you're saying that there's no difference when there actually is a difference. So in this case, misclassification has dragged us towards the null. Now, think of another case of misclassification. Again, we are still trying to compare an orange to an apple. But this time, we somehow mistakenly classified the orange as a rock. Maybe the orange fell into a slab of concrete and came out looking like a rock. So now we're comparing a rock to an apple. Of course, we say, oh, they're very different. Now, this is a case of false exaggeration, and the results are biased away from the null. So you can see that with differential misclassification, the same case scenario, one took us towards the null, the other dragged us away from the null, right? That's different from non-differential misclassification, where the result is always biased towards the null. So here, for example, we're trying to compare still an orange versus an apple, but we misclassify the orange as an orapple. This is a hybrid, an imaginary hybrid fruit that is a crossbreed of oranges and apples. So instead of classifying this as an orange, we classified it as an orapple. We also misclassified the apple as an orapple. So on both sides of a fence, we have misclassification going on to the same degree. Well, at the end of the day, what are we comparing? We're comparing an orapple versus an orapple. We conclude that there is no difference. That is biased towards the null, right? So the danger of measurement bias is that we never can truly tell which direction it's going to go. And also, there is no medicine after death for misclassification bias. This is why it is extremely dangerous to veer into the terrain of multiple imputation when you don't know what you're doing, because you can end up with results that are, you are literally jumping from frying pan to the fire. That's the point we're trying to make here. So again, remember that we said the three children of epidemiology: measurement bias, selection bias, and confounding bias, that at least we can have a silver lining with some of them. in this case, this is the case of selection bias, where we drew a sample from a population, but the sample is not, maybe people left in a way that was non-random, right? So some people left because they were triggered, or so males left to a greater extent or females left to a greater extent. And the end result is that the distribution in the sample is no longer that in the population. So that breaks the cycle of inference. We can no longer make inferences from the sample to the population. But at the very least, we can still make inferences from the sample back to the sample. So, and therein lies the silver lining with selection bias, right? All right, now, I want somebody to complete this sentence for us to show the silver lining when we have a case of selection bias. Because remember, we're trying to contrast that with measurement bias. That of the 3 children of epidemiology, the most deadly is measurement bias, and we need to pay attention to it very carefully. So can someone complete this sentence for us? In the case of selection bias.
Jeremiah.
Even if we couldn't do all, at least we could still do some.
Okay, thank you. That's one perspective. Another perspective, please.
Someone in the chat said everything, something. Even if we cannot do everything, at least we can do something. That's putting his words in sentence.
Okay, the hint is look at this cycle of inference and use that to answer the question.
You can raise your hand. No hand.
Okay, the hint is, again, remember, where is this cycle when we have a full cycle of inference? This is supposed to go from here to here, right? That's the hint.
Yes, Alex, you can unmute.
Okay, thank you. Even if we cannot generalize, at least we can still do inference.
Excellent. So even if we cannot make inferences from the sample to the population, at least selection bias at least allows us to be able to make salvage some kind of inference back to the population, right? At least we get something that, they say half bread is better than none. That is the forgiveness we get from selection bias. But when it's now a case of measurement bias, especially when it's superimposed on selection bias, now your data is now completely trash. Is there any silver lining in this case now? Because you have now suddenly used multiple imputation, and you have misclassified every single thing in your data set, which effectively renders it as trash. There's no silver lining here anymore. See, this is the danger of, this is how, measurement bias is so unforgiving, right? With selection bias, at least you can say, well, we can still make inferences to this sample. Misclassification or measurement bias in general is less forgiving, right? So this is why you want to be very, very, very careful before you even think about doing things like multiple imputation, because there's inherent danger of misclassification, and we can never tell the direction where that bias will go or the magnitude of that bias. So philosophically, both IPW, we haven't talked about IPW, but we're going to talk about it in a minute, create pseudo populations. We're going to come back to this slide later, but what I just want to emphasize here is the underlying assumption. Both IPW and multiple imputation assume that you have MAR, missing at random, right? Again, if you did not attend the past few classes, you may want to watch the video to understand fully the distinction between the types of biases. You really need to ground yourself in an understanding of those types, because without that understanding, you cannot manage missing data appropriately. So, again, remember the simple rule: do not jump from frying pan to fire, Multiple imputation has the potential to literally grab you and dump you into the fire because the assumption of ma may not be met, and you might also have multiple imputation, model misclassification. When we do multiple imputation, we use regression analysis. We are trying to predict. You might, for example, assume that the relationship between the variables is linear when it's quadratic, for example, right? So all of those kind of misspecifications can land you in trouble where you are literally then jumping from the frying pan to the fire. So in between multiple imputation and IPW, which again we haven't covered, but we'll come back to it, you should know that multiple imputation is the biggest problem you have. It's of all the methods to address missing values, this is the bigger problem you have. So you should be very, very cautious before just jumping into it. And don't just take at face value one software that tells you, oh, just one click and your missing value problems are over. That is definitely not true. So the big question is always, are we grounded in reality or are we just making up stuff? You can easily get into that territory of just making up stuff with multiple imputation if you're not careful. Now, let us critique this paper. So moral of the story, issues with handling missing values can even arise from top institutions, even at CDC. So this is a paper where they imputed state-level prevalence of achieving goals to prevent complications of diabetes in adults with self-reported diabetes. Now, the methodology was that there's multiple imputation for the outcome, which is self-reported diabetes. But what we want to focus on here are the limitations that are reported in the study. And as a way of just critically evaluating the paper, we want to look whether the assumptions of MAR are consistent with the limitations reported in the study. So first of all, it says that self-reported diabetes status and other variables might be subject to diagnosis, recall, and social disability bias, and that the methods of imputation for the methods applied cannot ensure that all bias was reduced, and that the estimates might be less precise than they would if those variables had been measured directly. There is so much to unpack from this, but we want to focus on two things. One, if the article is looking at diabetes, self-reported diabetes as an outcome, based on the limitations reported here, do you think that the assumptions for MAR have been met? Again, MAR is missing at random. Who wants to take a shot at that? So the question is simple. Do you believe, and this is just a debate, right? Do you believe that the assumption of MAR is met in this case? Based on the limitations that the individuals themselves reported. We're just basing it at face value from what they said.
No hand yet.
Okay. All right. Okay. Let's break it one at a time, right? If we have MAR, if MAR truly exists, which is missing at random, who can give us a recap of what missing at random means? In this case, what will it mean? Again, if our outcome is self-reported diabetes and we have a bunch of variables there, missing at random is saying that what? What are we saying is occurring in the data set? I think I have a visual here. Let's go back to MAR. So this is MCAR. So this is MAR, right? So again, remember, for those of you who are not here, we said a guy went missing. And we have two sides of the fence. One side is a guy who got missing. If we found out in any way that he is implicated in his disappearance, then we will say that he is involved, right? But if we find out that he's not involved, we will say he's missing at random from this side. On the other side of the fence, we have his neighbors, right? If we find out that they were implicated, we will say that it is Their involvement is not random. But if they were innocent, we'll say this was random. When you have random here, the guy was not involved in his disappearance. And random here, then we say you have two randoms. So it is missing completely at random. That is MCAR. And this is the assumption you need for listwise deletion. Then, missing at random means you have just one random, right? There's random here, but not random here. In other words, we're saying that self-reported diabetes, the missingness for it, is associated with other variables in the data sets, right? But we are saying that there is nothing about diabetes in of itself. There's nothing about having diabetes in of itself that will make someone have a missing value. So in other words, the guy is not implicated in his own disappearance, but the neighbors are. So in other words, you're not having a missing value, or you're having a missing value for self-reported diabetes, maybe associated with age or gender or other factors. But there's nothing about having diabetes in of itself that would lead one to have a missing value for diabetes, for self-reported diabetes. So that's what MA is saying. It's saying that there's a systematic pattern of missingness. There's an association between other variables, but there's nothing about that status itself that would give rise to missingness. So this is MA. This is the assumption we have for IPW and for multiple imputations, right? So we want to keep that in mind. So let's go back to the paper. The paper here says that the limitation here says self-reported diabetes status and other variables might be subject to diagnosis, recall, and social desirability bias. Full stop. Now, this limitation here, the question is, does it or does it not contradict the approach or the assumptions that the authors have stated? Remember, the assumption is that data are missing at random, that there's nothing about being a person living with diabetes that would make you have missing values for diabetes. That is the underlying assumption for MAR. Now, is there any part of this statement that contradicts that assumption?
Jeremiah Paul.
Okay, I think the part that contradicts the assumption is other variable being subject to diagnosis.
Okay.
Because since the assumption is that the diabetes status has no other link that could have caused it, but now they are reporting that there are still other variables that could have led to the diabetes if being diagnosed.
Okay. Alrighty. Any other thoughts?
Yeah. Yes. I think this with the limitations here, it shows that ab initio that the patient or the subject could also be implicated in the missingness of data as secondary to their forgetfulness, that is recall bias, and it could also be as a result of sorry, let me see this. Okay, but in conclusion, what it means is that the subject or the missing data itself is implicated because it could be based on the fact that the variable was the disease was not diagnosed, or there was a problem with recalling of the event or the diagnosis, or any other social factors that will not make the patient or the subject to confess or to affirm that he or she has diabetes. So what it means that this already contradicts MA, because the subject or the data point could be implicated or is implicated in the missingness of that data.
Thank you very much. I think we have other hands up.
Yes.
Thank you so much.
Congo.
Hello?
Yeah, we can hear you
Yes,
clearly.
Yes, sir, I was thinking on this dimension. If this diabetes status will be kind of measurable, maybe a medical tool will be used, then will be missing at random. But now, it being that it's a self-reporting, and with the other variables that might affect that self-reporting, then I think it is not necessary to say it is missing at random. That's my opinion.
Okay, thank you. Yes, any other thoughts?
Taiwo.
Thank you very much, Prof. I think from that statement, we can say that the diagnosis of diabetes itself can contribute to the missingness, in the sense that the diagnosis was not based on objective measurement during the study. It was based on what people could report. And we know that diabetes can affect memory. So I think that the missingness can be contributed to by both the diagnosis of diabetes and by other things such as social desirability and other things that were mentioned there. So I think this will fit into missing not at random instead of missing at random.
I really love that angle you brought from the perspective of diabetes having an impact on memory. That is a really powerful point. And that again indicates that once you have something about the question contributing to missingness, well, it's no longer MAR. Yes, there are still some hands up. Let's hear other perspectives too.
Abayomi.
All right, thank you so much, Prof. I think it's very, very plain that when a process is not validated, that means the results will be faulted. So contradictorily, the two statements that is mentioned there is saying that, yes, the process for which we used to collect data is faulty. Then why can we now say that, yes, that we can ascertain that the result that we got from the data is complete, is okay? So it's contradictory in that sense. The process does not guarantee the result. So why do you then can vouch on the results that you've gotten from such a method? I think that's the basic thing there.
Okay, thank you very much. Now,
we have one turn.
Okay, go ahead.
Daniel.
Yes, thank you, Prof. Interesting point we have come to here. My thinking is that the subject is actually involved in the actual missing of the value, what we are looking for. And this is because the recall occurs in the subject himself, and the social desirability of his condition might affect him being able to say that he has diabetes. It influences, so he's actually involved in the missingness of that value. Thank you very much.
Thank you very much. Excellent answers. Again, remember, is there a statistical test to rule out EMNA? Because again, for us to proceed with this, we have to first rule out missing not at random, right? And again, just to go back to the picture. Oh, was it forward? So remember that there's no objective way to prove that this guy did not implicate himself. The only way we can make that determination is through theory, through explanation, and say, well, as somebody who has been involved in investigating missing people, I think that this is not a statistical thing. This is where you come up with explanations as a clinician or as an expert, right? And so that's one thing we want to keep in mind. But I also want somebody else to critique this part here. There is something here we're just leaving completely open. The claim here says that the state level estimate might be less precise than they would be if these variables had been measured directly rather than relying on multiple imputation. Can someone challenge the veracity of that statement?
Jeremiah.
I didn't know I was still raising my hand. I was having another opinion concerning the MA initially. I didn't know I didn't close my hand again.
You can go ahead and share your opinion now that you have the floor.
You mean for the
whatever
MA?
whatever you wanted to say. Yes.
Okay. I was trying to say the statement actually contradict the MA initially, because miscellaneous completely and random would imply that the missingness is unrelated to both the observed and the unobserved data. But the limitation mentioned in the report suggests that the missingness might be related to the observed data, which is more consistent with my assumption. But on the other hand, it has no objectivity to say that the missingness is unrelated to other data, because it has explicitly said that it could be subject to diagnosis and other factors. So that was what I was trying to bring about before. So I didn't lower my hand.
Of course, excellent perspective. But just to re-echo that the assumption for multiple imputation is MAR, not MCAR. So missing at random. Missing at random means that the missingness is associated with things inside the data set, but it's not associated with things outside the data set. Of course, that is obviously, like everybody has excellently stated, things like recall bias and social disability bias are not things that are in the data set. They're things that are outside the data set. So you can't exactly tell us that you did multiple imputation and then in the same breath tell us that the outcome you just imputed is related to things outside the data set, which as a reviewer will make me scratch my head and say, I am very confused by your approach, or it makes it clear that maybe you do not have a solid understanding of the assumptions that would warrant the use of this methodology. So let us not be obsessed with methodology. Sometimes people use methodology just to sound fancy, right? We really want to understand the assumptions that underpin whatever we do. Now, I would like someone to challenge this claim here that the state level estimates that the results from the paper might be less precise than they would have been if those variables had been measured directly and not imputed. Any thoughts on that?
Yes, sir. I think there's misappropriation of term. When they say less precise, it would have rather be less valid, because when we talk about precision has to do with the number of the sample size, right? And by doing multiple imputation, it means that everybody that was originally that is expected in the sample size is there by one way or the other. But introducing multiple imputation, it means that one, you probably have committed differential, or no, let me say, any kind of whether differential or non-differential measurement bias, but that there's bias already, measurement bias, because you introduce multiple imputation. That will affect validity, right? Not precision. So I thought they would have rather said the result might be less valid than say precision or precise.
Okay, thank you very much. So for that statement, I'm not going to go ahead and give it a true or false grading. I'll say maybe, right? It's true that statistical software, what's happened behind the scenes is that your software is saying, well, we are just guessing this thing here. So you know what? I'm just going to give it a wider confidence interval. So wider confidence interval means less precise. But the thing is that you are comparing that scenario to a counterfactual. You're saying if they had been measured directly, the confidence intervals will have been, narrower. But how do you know? We don't know. So it's hard to answer that empirically because we can't. And then the last point I really wanted to make before we move on is that if you claim that so horrible because of self-report, then it begs the question of why are you using multiple imputation? Remember, garbage in, garbage out. Multiple imputation is a prediction exercise. We're predicting the next value based on what we have seen. So you've already laid the argument very clearly that this data are complete garbage. And then you tell us that, well, we use this garbage to make predictions. Like that's a real head scratcher there. So the point I'm trying to make is that don't just rush into a statistical procedure, right? It's best to understand. The most important thing is to understand the foundational elements. The simple things, the non-complicated things are the most important. And that's why we're focusing this class purely on just the intuitive understanding of what's going on, as opposed to, writing code. And anyone can write code. We need to have a foundational understanding of what we're doing so that we don't make mistakes in interpretation or application of methods. All right, we've talked about this already. And then the team number 3 was the inverse proportionality weighting. So is this valid? Is it precise? This was a scenario where the one guy was made super large to compensate that he was alone.
Yes, Alan. You can unmute. Okay. Benjamin. Benjamin.
Yes, good evening, Prof. I feel it's neither valid nor precise.
Okay, remember he got first position here. Does that change your answer, or you still stick with that answer?
I'm still with the answer.
Okay, all right, thank you very much. Any other thoughts or opinions?
Jeremiah.
Okay, thank you. I would say it's actually not precise, but it could be valid.
Okay.
Valid in the sense that the measurement you will get will give the actual measurement of when it became a larger human, but not precise in the sense that that is not the actual weight that he possessed as a single person.
Okay.
So
we're judging.
That is my suggestion.
Right, thanks. But remember, we're judging this by what is in this, what he wrote. So we want to focus on what he wrote.
Amos.
So, looking at what he wrote, looking at saying, I must be the world greatest a woman, and how possible will you be a world greater man and become a woman? I mean, normally, so he's trying to be precise and just referring to himself based on what he thinks. He's not trying to look at the proportionality within it. So for me, I personally would look at he's trying to be precise on everything he do. Okay, thank you.
Thank you very much. All right, one last opinion.
Yes, sir.
Harrison.
Yes, to me, is not valid and it is not precise. The statement here is a mere assumption. It could be first, it could be the last. It's only assuming, and so it's not valid. Okay. And looking at what we see, is not precise. Must be clear.
Okay. Right. One last question, and then we'll move on.
Abdul Samad.
Okay, Professor, I think that it is valid because it has internal validity because it is explaining the weight by giving it weight. It is giving the same answer because it is internally valid, but it doesn't fulfilling the sample size of the sample. So because he is only one guy instead of the two, so it is not precise. So I would say that it is valid, but not precise.
Okay. All right, let's move on. So it depends on how you view it. If you're very literal, you might say, oh, well, how can he claim he's the greatest in the world? Well, but if you don't take it literally, I take this to be valid because he just finished the fight where he won. And he's like, I must be the world's greatest. I'm a one-man army, right? Yeah, he came and he conquered. So if you're not taking it literally, you can say, yeah, it's valid, but it's not precise because it's not clear. And, so that's what we understand in this. But the bottom line is that with inverse proportionality weighting, we give this guy a bigger size, right? The bigger size so that he represents himself and the guy who was supposed to be there, but is missing. Now, the question then is, how big is too big? We want to make this guy big to represent the other guy, but how big should we allow this guy to be? Well, the problem with more weight is that you have more problem, both physically and statistically, right? If we give this guy weight, the problem is that he starts expanding in a manner that is disproportionate. So not all parts of the body expand the same. Maybe his stomach gets much bigger and he becomes unstable, right? And so him growing bigger and bigger becomes a problem because he becomes more and more unstable. So the question is, how do we address this? Well, we can address this by putting the cap to his weight, to the size he can grow, right? And that's the concept of stabilized and unstabilized weights. When we use stabilized weights, we are trying to acknowledge that, well, when you have very massive weights, it's never a good thing because it makes the whole analysis unstable. You start having very wide confidence intervals. So what do? Well, we impose a cap to which you can grow. We talk about a stabilizing factor. The stabilizing factor is simply a number that will multiply against the weights that we just created. So for example, we can use a number like, let's say, the prevalence of the exposure, let's say 0.5. So that means that the weight will always be multiplied by 0.5 so that it becomes smaller. So you have to understand it not necessarily in the semantics, but philosophically, what are we trying to achieve or what are we trying to prevent when we introduce stabilizing factors? It is this phenomenon that when somebody grows so big, their weight becomes a problem. And in the statistical concept, it becomes a problem because the confidence intervals start getting very large. So it's not that the guy is big that is a problem. It's that he's differentially big, right? Some parts of his body are bigger than others, and that makes him unstable. If he were just growing proportionally big, oh, like, good job. But it's that it is differential. And by the way, in epidemiology, whenever you see the word differential, it's always a bad thing. So that is why we use stabilizing factors in analysis. Again, focusing on the big picture and not necessarily on the code. We just need to understand intuitively what's going on. Now, there's two very, very similar concepts we need to understand. That's IPW, which is inverse proportionality weight, and non-response weight. You will hear a lot about weight, that there are different types of weight. So you need to understand how they are similar and how they are different. So this is what IPW is trying to do. It's trying to correct for non-response that comes from inside, which is missing values, which is what we're talking about here. But you also have non-response weights, which is trying to correct for non-response outside the study, right? So what does that mean? Well, we did our survey. You might have a complete data set, but you look and you're like, wow, 25% of my sample are males compared to 50% in the census. It means that many of the males outside did not answer the survey, right? So the non-response in this case is outside. In this case, the non-response is inside. Either way, you have to correct them with weights. They are two sides of the same coin. So you need to understand that philosophically. next week webinar, we're going to focus a lot about survey design, and it's, primarily complex surveys. It's not just simple surveys, right? We're going to talk a lot about concepts about weights. How do you measure them? And so by the end of next week's webinar, you would, next 3 weeks rather, you will surely become an expert in all of that. But the bottom line here is that you should understand that IPW is, similar to non-response weights, but doing somewhat different things. And that's the relationship between the two of them. Now, whether it's non-response weights or IPW, whether you're trying to control for missingness inside or missingness outside, they are both trying to achieve the same thing. This is your data set with its missing values, whether the missingness is from inside or from outside. What they're trying to do is to say, okay, we're going to force this sample to look like what we think the population is supposed to look like. That is what weights do. Weights take your data set with its missingness and forces it to assume the characteristics of the population itself. That is what's going on behind the scenes. So we need to understand that. So both IPW and non-response weights, they will both create a new variable in your data set, right? So you need to understand intuitively what those values mean. If you have a weight of 3, it means that that individual stands for 3 people, like himself or herself, right? So that means they stand for themselves and 2 other people. A weight of 30 means that the individual stands for 30 people, including themselves. A weight of 300 means the individual stands for 300 people. So my question to you is, can you have a negative weight? Or can you have a weight of 0? What are your thoughts?
Okay, someone said no.
Okay, that's correct. So you should have an intuitive understanding of why that doesn't make any sense. So if you pick a data set, you're analyzing and you see a weight of 0, that makes no sense. Like how? The person at least should have stood for himself, first of all, that is just some foundational basic things that we all need to know. So how does IPW differ from non-response weights, at least visually? So here is our sample where there's no bias, or this is a random sample that doesn't need treatment. There are 2 guys here. With non-response weights, you might have 2 people too, but what we're saying is that the non-response is from the outside. So we have to make this guy bigger to represent all the guys who are outside that look like him, right? So it's possible we started the data set with these 2 guys, and now we have to assign extra weight to 1 guy, right? So that is the structure of non-response weight. That's what we're doing with that. Raking or IPW, however, is specifically for missingness inside, whereby the individuals who are not missing, we give them extra weight so that they now represent all those people who have missing values. We're going to cover a lot more of this in the next webinar on complex survey design, but at least it's helpful to have an intuitive understanding of what we're trying to achieve or what is going behind the scenes. So now, if you generate a process that has multiple weights, you can only have 1 weight in your analysis. So the final weight will be equal to the product of all the weights. So weight 1 times weight 2 times weight n. That will be the final weight. So in this, because it's possible for you to have both missing values. So imagine here that we're discussing issues of missingness, right? And take the population as the pot here and the sampling as the cover. So when you don't have a cover, when there's no sampling frame, that means that your study is non-probability based. When there is a cover, that means that there is a sample, it's probability based. At the end of the day, the final result is what we're going to evaluate how the results were generated in terms of the validity, right? The question is what is in the plate, the same as what was in the pot, right? Ideally, what is here should be what was there. The bottom line is that don't worry only about missing values, right? Worry also about things that are missing outside the study. That's the point we're trying to make here. So it's possible that you have a case of sampling where you have a perfect sampling frame that covers the port completely. It's possible that in that same scenario, you have missing values. So now you can't just say, well, because the sampling frame was perfect, I don't have to do anything. Well, you have to worry about issues of frames and issues of sample size or missingness. That's the point that we're trying to make. Don't just fixate on missing values. You have to worry about bigger issues that afflict your data set as well. Here, this study has a small sampling frame that does not cover the entire population. So you might have entire segments of a population missing. And at the same time, you have missing values to worry about. So don't just fixate on the missing values. Worry about issues of study design as well. And here you have a sampling frame that is, covers the population, but there's non-response bias. It's kind of leaky, right? And at the same time, in this case, you also have missing values. So here you have to worry about non-response weights, and then you have to worry about the weights or however you're going to control for missing values. So moral of the story, don't just worry about one thing. We are going to announce an 8-week course very soon on that will focus purely on writing code. That how do you actually implement this thing? So that is when we're going to cover more of the statistical approaches to solving these things. But now we're just interested in the high level understanding of what these things mean intuitively. Now, beware of asking the wrong question. Question most people ask is, oh, so what percentage of my data should be missing and then I can still use it? That's a very unuseful question or very unhelpful question to ask. The question lacks context. The question assumes that all missing data are equal. And then there's no universal threshold. What answer are you expecting? 5%, 10%? What if your data set was only 50 people and we said 10%? Well, so there's no answer to this question because the question doesn't make sense. The only way to look at such questions is through the lens of, again, validity and precision. So here is the most important slide of all of the slides we've talked about. This is a framework that I created to just help you think of how do you make decisions in relation to missingness. So the first thing you want to ask is missingness consistent with MCAR, right? That's the first question. If the answer is yes, then you can assume that validity is assured if the data were valid at the beginning. So that means that if you had the data set at the beginning that was drawn at random and that was valid at the beginning, you can assume that it's still valid, even though you have missing values. Why? Because the missingness is consistent with MCAR. Note the way we framed it. We said, is missingness consistent with MCAR? We did not say, is data missing as MCAR? Because you can never prove that your missingness is MCAR. You can only say it looks like MCAR. You can't say it is MCAR because you cannot prove it definitively. So that's, so pay attention to the framing as well. Now, if the answer is yes here, then the next thing we need to worry about is issues of precision. Remember, you always have to worry about validity and precision, the two of them, not just one of them. So if we conclude that, yes, missingness is consistent with MCAR, the next question is, are issues of statistical power or precision a concern? You might be doing an analytic study where you have to compare two groups, and you want to make sure that obviously the study is powered. So if you were to do a listwise deletion, you might end up with a scenario where you no longer have power to detect difference between the two groups. So when it's comparative studies or analytical studies, we talk about power. Or it might just be a descriptive study you're doing, but you still have to worry about precision. And my confidence interval is going to be too wide because I have done listwise deletion, even if there is validity. So again, remember, you have to worry about validity and precision. If you're worried about that, then you can impute, because again, under MCAR, if you can be confident that the data are consistent with MCAR, then imputation should give you results that are valid. Otherwise, if you're not concerned with issues of power or precision, then you can do a listwise deletion. That means that individuals with missing values will be deleted, but you don't even have to worry about issues of bias because the people leaving the data sets and those remaining in the data set are exchangeable. There's no systematic difference between them. And so your results are still valid, they're still generalizable, and should you have enough numbers, they are still precise. So that is the flow in this direction. The next flow is you find out that no, the missingness is not consistent with MCAR. The next question you have to ask is, can I rule out MNAR, right? Can I rule out that data are not missing, at random, not at random? Now, this is the hardest question ever because remember, there is no statistical answer to this. There's no statistical test to demonstrate that, there's MNAR or not MNAR. You have to use subject matter knowledge. So remember that diabetes study? These are the questions you have to ask yourself. Is it fair to conclude that the missingness patterns have everything to do with things inside my data set, but nothing to do with things outside the data set? Well, if you cannot answer that question, then that is dead on arrival. You cannot use IPW, you cannot use multiple imputation, you cannot use any of those techniques, right? Because they're all hinging on the data missing at random. And you can only conclude that they're missing at random if you can rule out MNAR. If you can't rule out MNAR, you can't come to a case of MAR. So in this case here, can you rule out MNAR? The answer is no. Well, that means that validity is threatened. Even if it was valid at the beginning, it is no longer valid now. There's no guarantee that it's valid now. However, if we can rule out MNAR, that means that we have concluded that they are not MCAR and they are not MNAR. The only option remaining is MAR. So at that point, we can conclude that there is an assumption that data are missing at random. So what does that mean? It means that we can impute. It means we can use IPW. Those are very strong assumptions. And this is the process through which you must go if you are thinking of using any of these techniques. So please, there's a lot of bad advice and a lot of bad software out there. Don't just trust any software that just says, oh, just bring your data set and just click this button. This is not something that any software can do for you because MNAR cannot be determined by statistics. It has to be determined by subject matter knowledge and your understanding of the local context. This is why it has to be a human-driven decision. So now you have found out that you cannot rule out MNAR. So what does that mean for you? Then you have to look at, okay, now do I just have to throw away this data set or can I just use it for something, right? Now, because now we have proven that you cannot assume validity. So next question is, okay, well, I don't care about validity, but is there precision? If there's no validity and there's no precision, then what are we talking about? Then that means we have to toss that data set into the bin. So we've established there's no validity. The next question is, all right, can we look for precision? Is there precision? And there are many standards that we can use to assess precision. We can use NCHS guidelines or rules for precision. It requires that you have at least 30 individuals per cell. That's one guideline we can look at. And then from a causal inference perspective, we need to make sure that there is positivity. That is a very, very important assumption for, well, primarily causal inferences, but we can also generalize it to research in general. We should always ensure there is positivity. Positivity means that in every group, the probability of observing the outcome must be a positive number. That's why we call it positivity. It doesn't mean that it has a positive vibe. No. It means that the probability of observing the outcome must be a positive number between 0 and 1, but not including 0 or 1. So it means that in any group, if I just pick any group, let's say males, and let's say the outcome is diabetes, I cannot have a scenario where all males have diabetes or all males do not have diabetes. Then the assumption of positivity is violated because the probability of observing diabetes among male is not a positive number that lies between 0 and 1, but not including 0 or 1, right? So the assumption of positivity is violated, right? Those are measures to ensure that we have enough people in our study to analyze it. So what if you now find out that, okay, validity is not met because of MNAR and precision is also not met? What can you then do? Well, you can either trash the data set You can consider it not fit for use, at least for that particular use case. You can analyze it qualitatively to inform further research. But surely you cannot analyze it and make valid inferences from it that would, that would change or it won't pass through peer review if you have solid peer review. So the moral of the story here is this abstract from, I couldn't frame this better. The last sentence says that finally it should be realized that preventing to have missing data, it is always better than the treatment of missing data, because the treatment is very complicated, right? And it requires deep subject matter knowledge and requires deep context or contextual understanding of what's going on, right? So it's not something you want to engage in if you can avoid it. So that's the moral of the story. So the moral of the story, when you are setting up a data collection, pay very close attention so that you never have to, by the time you're looking at this framework, you're already in a sinking ship, so it's better not to come to this scenario at all than to come here and start wondering, do we have MNAR or whatever the case might be, and and be very wary of multiple imputation. That's the moral of the story. All right, we're going to stop here and take questions. That's the end of the class. And again, emphasizing that the MVP is context. We need context. All righty, we'll take questions now.
Thank you very much, Prof, for the brilliant presentation as always. But before question, I would be sharing the attendance link. Remember, this is the last section. Ensure you complete it if you want to get certificates. The link is in the chat now. Jeremiah.
All right, thank you very much, Prof, for your deep knowledge on missing data. My question is in relation to weights, whether we have negative weight or a zero weight. So I want to ask if in a study you set eligibility criteria, what weight will you be given to the people that did not meet the eligibility criteria?
Okay, so you're not the one who is, okay, so your question kind of suggests that you're the one assigning the weight. You're not the one assigning weight. The computer assigns the weight for you. So let me quickly show you how that works. So that that would be the best way to answer that question. So now the process of generating weights is extremely, extremely complex. The good news, however, is that on the Chisquares platform, we really solved that problem through automation. So you will never have to worry about, geez, how do I create weights myself? So let me show you how that process works, because it is not something you do manually. It's, and the process for addressing non-response weight is called raking or iterative proportional fitting, because it's iterative, as the name implies. In large surveys, most of the US large national surveys, we use multiple variables to adjust for weights. And let me just show you quickly how that works. Let me pick a survey that is closed. So to implement weight, you've collected your data. So in this case, this was the last survey we did last week. Your survey must be closed first, and for obvious reasons, because you cannot have missing values for weight. You know that the data is very sketchy. If you look at there are some variables that you look at and you know that, okay, this is fabricated data. This is clearly fabricated, or this individual, there are just major red flags with this data. Imagine looking at a column for weights and you see missing values. It's like, that makes no sense. You see negative values. You see, none of that makes sense. It's not consistent with mathematical reality at all, right? And so that should create instant red flags for you. Or you start seeing character, like, values that are not numbers. That makes no sense whatsoever. And that should make you question the authenticity of that data set. So in this case, let's see how that process works. So in this case, our survey is already closed. And so what we'll do here is come to data access and insights. Here you can download the data set and, whether it's, but what I want to do here is weight data, right? I have a lot of processes going in the background. All right, so weight data, and I'm going to click on new calibration weight, right? So all of this is automated. You're not the one assigning weight yourself manually. So you then select the variables you wish to weight on. So you assign the name of a variable. So remember, after you finish creating the weight, you should have a variable in your data set called weight, or whatever name you choose. I can call it my weight or my weight, whatever name you want to give it. That variable will be the one that will have all of the weight variables that have been created. Now, next, you have to select the variables that will be used to weight the data. When you're doing a survey, a large national survey, for example, you must think about issues of weight before you start even collecting data. When you're creating your questionnaire, that is when you should be worrying about, okay, how am I going to weight the data? It's not when you've collected the data, you now say, okay, oh, I found out that there is non-response bias. Geez, what am I going to do now? You don't wait for problems to occur first before you start worrying about them. So let's say I want to weight the data by age. And let's say, okay, now the platform automatically will check whether you have, enough responses. So in this case, you don't have responses, you have categories in that variable age, but you don't have responses in them, right? For you to weight the data, it means that the variable you are using in your data set must exist in, let's say, the census. The categories in your, for example, age variable in my data set must be the exact same thing as the categories in the census. And that if in my survey, I stated that the age has values of male, female, and other, that each of them has responses in them that meet NCHS guidelines. The platform enforces all of those things so that you cannot make a mistake. And if you're going to make a mistake, it's going to tell you. So let me find it that another variable that I could just use. All right. So in this case, I've selected one variable I want to weight on. Now, what I have to do is I have to provide the percentages for individuals, in these categories from the census. I can say from the census data, it's clear that this percentage is, maybe 25% and so whatever. Once I'm done with this variable, I can click done with that variable. And that's how the weights are created for you automatically. So it's not something you do manually. That's the bottom line. All right, next question. And again, we're going to cover all of these things in the session on sampling next week so that you have a first-hand experience of how that works.
Let me read a question from you too. Does it mean precision is always based on sample size, please?
Yes.
Okay. There's another question in the chat. If we observe that some participants did not fill completely a questionnaire in a survey, is it right not to impute data from the incomplete questionnaires? Example, if 50% of the questionnaire was not filled, or we should impute data from all the retrieved questionnaire data, the questionnaire before we attend to the missing data.
Well, the whole point of this 3 weeks is to say you should do the exact opposite. You should definitely avoid that suggestion. That is the point of the three weeks we've had. That you can't just say, well, I have missing value. So what I'm going to do is just put in some arbitrary numbers. That is a very dangerous thing to do. You are creating just garbage. That's no longer data set. It's not valid anymore because for you to do multiple imputation, there are assumptions. So the whole point of this 3 weeks is to say that is a no. So the moral of this, is that you should always try and address issues of data quality before you collect data. You want to avoid medicine after death.
Hello, Prof.
Hello.
Yeah, thank you very much for the wonderful session. And I have a little questions, even though it is a challenge for me. So I would like to the Prof to address it in a just short answer. A colleague sent me a verified or already collected data. So I was observing the data. I realized that there are some missing value in the data, and I try my best to see that I rectify the issues, but it is the thing like got out of my hands. And one things I realized is that he used uh, some styles like a skiffing style while collecting the responses. So what I want to know is that during the analysis, like I try to do the analysis like descriptive for the ages. So I realized he collected the total sample size of 557, but I saw the results or the software creates another line which really wrote 999. So I'm not sure from where this result is coming from. I try to read online. So though I cannot even reach out to him, so I just want to know how can I address this issue. Thank you very much.
Okay, thank you for your question.
Yeah, thank you very much.
Appears Prof is having some technical challenge. Let's give him some few minutes.
Okay.
So, but you can keep dropping your questions in the chat or keep your hand raised.
Hello, sorry, can you hear me now?
Yes, we can hear you, sir.
Okay, so the question was that, you collected data and you have 500 individuals who are eligible, but whatever software you're using shows up as 900. Well, that could be perhaps because you have eligibility criteria. If you have screeners in your survey, some individuals may have answered those screeners but may not be eligible, but the data set obviously will still capture them. So you have two numbers here. Now it's all the individuals who attempted to do the survey at the beginning and those who attempted and are eligible. So obviously those will be two conflicting numbers. One will be bigger than the other. So that may be the explanation. But without additional context, I cannot say for sure. But that could be the reason why you have those two conflicting numbers.
Thank you, Prof. Abubakar, I hope you are clear now. Adishwa, your hand was up.
Yes, thank you, Prof, for this educative webinar. I was the one that posted the question on not filling some questionnaire completely, but I felt the person that read it did not understand completely what I was trying to pass across. You know, when you are conducting a survey, let's say in a situation you send the questionnaire to people to fill, and the questionnaires are returned, and you discover that some of the questionnaires, maybe 50% of the content were not filled. And at the level of determining your sample size, you've already added non-response rate to it. Isn't it right not to enter those incompletely filled questionnaire into the software for analysis when you know that you will still be able to get your the minimum sample size, and that those ones that you are excluding, they are just the extra percentage non-response rate that you added to the questionnaire? Do we have to enter everything and analyze and then start dealing with missing data? Is that not burdensome to me when you know you can still afford to have your minimum sample size at the end of the day? Thank you.
All right, thanks. Thanks for the clarification. So again, you always have to worry about the twin problems of validity and precision. Those two things must be at the top of your mind. Your concerns only address half of that problem. When you say, well, I have enough people, I think I'm good to go. Well, you may be good to go from a perspective of precision, but not from a perspective of validity. Now, if you are drawing a representative sample, and let's say the sampling procedure said, go to this house and go to that house, or go to this neighborhood, and you go exactly there, well, you can't now just toss out some individuals because of some issues, because they were selected probabilistically. Now, if you toss them out, you should be aware of the consequences. That means that your sample is now automatically a non-random sample. So you should be aware of the implications. And as far as you are aware of them and that you can live with them, that's fine. But once you have a random sample that you just discriminately tossed out some elements, that process automatically turns it into a non-representative sample. This is why in national surveys, if we have drawn a sample from a sampling frame, sometimes we end up going to the same house over 100 times, because the sampling procedure told us that that person's house must be selected. If it means going there 100 times, then we have to go there 100 times, because we can't just say, oh, you know what, this house is giving us problems, so we're going to switch it out for another house, because no. That's not how random sampling works. If it was selected probabilistically, then we must go there. And if it was already collected probabilistically, we can't just toss it out. It has to remain. And once you remove arbitrarily, that means that your sample is now non-random. And if you can live with that, that's fine. As as far as you are aware of it and you can live with it.
Thank you, Paul. Let me read another question. Please, what do you mean by weighting a data? Why do we have to weight some variables? I'm a bit lost.
So weighting of data, you should definitely sign up for our next recurring classes, our next webinar series, which will be the next 3 weeks, where we're going to cover all, everything about weights and sampling. But in a nutshell, we weight data to make it generalizable, right? We collected data and we realized that, geez, our sample is not representative. Well, what can we do? The data is already collected. It's not as if we can go back to the field and draw another sample. Well, this is when statistics comes to our rescue. We use statistical procedures to force that sample to look like a parent population. And that's what happens exactly in weight. It's a mechanism where we can allow the sample we have that is non-representative, that is biased, to become more like the parent population from which it came, using statistics.
Thank you. Daniel. Owusulu.
Hello.
Yes, we can hear you.
Yes, very clearly.
Yes, Prof. Please, I need clarification. That was based on what the other speaker the question she asked. Is non-response rate the same thing as missing variables? What do I mean? You have a questionnaire. There are 30 questions, and you had response for only 20, maybe in the same sample size. I thought that is where we talk about missing variables. Non-response rate is more or less the sample size. So I don't know. I think I'm a bit confused.
Okay. And again, these are issues we're going to cover in the next webinar clearly. But to answer your question, response rate, which, by the way, that's such a horrible term because it's not a rate. But anyway, I digress. Let's stick on topic. Response rate, we calculate response rate by saying, okay, individuals who responded over the total population that we reached out to. I reached out to 100 people, 50 of them responded, right? The response rate in this case is 50 over 100, which is 50%. Now, like I said earlier, in epidemiology, we always start to worry when we have the word differential. Now, when we have differential response rates, we start getting worried. Let's say that among males, the response rate was 50%, but among women, it was 20%. Now, the problem is that the response rate is now differential. If it's non-differential, if everybody has a response rate of 30%, nice and good, there's no problem. But once the word becomes differential, we start to panic here because we don't like that word in epidemiology. It means that there is bias, right? So your sample size, your data set could have 0 missing values, and yet you will have issues of non-response bias because you can only know about non-response bias by comparing to the outside. It's not only looking at what's in your data set, but looking about how did these people come in here? What is the denominator? I hope that explains. But we're going to address all of these things in great detail in the upcoming webinar on complex survey design.
Thank you, sir. And with another question. In a paper-based survey, non-response simply refers to those that did not return the questionnaire. How do we calculate non-response rate for online survey? Does one report 100% response, or can incomplete responses be classified as non-response?
You cannot calculate, you cannot calculate a response rate for a survey that is non-probabilistic, right? So just a little context of why we call things certain way. When we say a survey is probability-based, probability means that there's a number at the top and a number at the bottom, right? That is how you calculate the probability. You say there's a numerator, let's say 2 over 10, which is 1 over 5, right? That's the probability is 0.2 or 0.5, whatever it is, right? So whenever we come out with the probability, there's always a number at the top and a number at the bottom. Now, the number at the top is what is in your data set. So let's say you have 200 people in your data set. That is the number at the top in that calculation. Now, you must have a number at the bottom for you to calculate the probability. When you don't have a number at the bottom, we call it a non-probability sample because there's no number at the bottom. So we can't calculate the probability. When you have a number at the bottom, we can calculate the probability, and that's why we call it a probability sample. Now, you can only have a probability sample if you had a list of everybody who was supposed to take the survey. In other words, you have a sampling frame. If you don't have a sampling frame, you can't know the number at the bottom, which means that you cannot calculate a response rate. So in a nutshell, whenever you have a web survey just put on Facebook or you blast it on whatever, well, the problem is that that is one way to easily know whether you are dealing with a probability sample or a non-probability sample. Do I have a number at the bottom? Yes or no? If you don't have a number at the bottom, well, you can't calculate the response rate because it's a non-probability based sample. Next question, please.
There's no question in the chat. That's the last question.
All right, awesome.
Raise your hand if you have before, so please. Okay, it appears we are all good.
All right. All right. Thanks, everyone, and have a great weekend.
Cool. The hand just popped off.
Okay. All right.
Julie.
Okay, good evening, Prof. And good evening, the coordinator. Thank you so much for the lecture. So in practical terms, when we have a data and we are entering it into, okay, let me put it this way, a data that has been sent in an Excel sheet.
Is that me or is that the speaker? I can't seem to hear them again.
I think it's the speaker. I cannot hear him as well.
Okay.
Hello?
We lost you for a minute.
Yes. So I'm just saying that sometimes let me use myself as an example. Having to see a data set with so many missing values, sometimes I get frightened. So I just want a guide. Do I go ahead, first of all, filling those boxes with any not available? Like everywhere there's missing data, irrespective of the number, because sometimes the number of missing data is so scary that you feel like just going ahead to analyze those that does not have missing data. Do I go ahead first, put in any in all those boxes before trying to identify the cause and probably run analysis? Thank you.
Thanks. You want to collect data, you don't want to enter, delete, alter, tamper, or do anything to that data set because you have compromised the integrity of the data, right? So no, do not enter NA. The problem with doing things like that is that if NA becomes a valid entry, if you're using, for example, that differences in how different software, interpret missing values. For example, in R, and NA is missing. In Python, it's NaN. In Stata, it's just an empty space, and differences exist with, other software like SAS and all of that. So don't enter anything. That's a short story. Don't enter, delete, do anything that will tamper with the data. When you are setting your survey, you want to make sure, this is why you want to make sure that whatever platform you're using to collect your data is fit for use. Any software that is robust enough should be able to automatically track missing values and to classify the kind of missing value you have. Because the problem here is that you are entering NA everywhere, but there are so many types of missing values, right? You do not, at the time you have the data set in your hand, you don't know where the person was missing because they were ineligible or they were skipped or it was a partial response or it was from whatever cause. You do not know that, but you need to be able to discriminate between the different types of missingness, right? So the moral of the story, please, when you're collecting data for a serious research purpose, you should make sure that whatever software you're using meets minimum standards. This session is not about endorsing any software. Whatever software you're using, it's your responsibility to make sure that it meets minimum standards. Otherwise, you get stuck with a scenario of medicine after death where no one can help you. I hope that is clear. All right, any other question?
No question.
All right, awesome. All right, thanks everyone. Have a great weekend.
Thank you, sir.
You're welcome, yeah.
Okay. A lot of people are asking about the attendance link. I will share now. Please check the chat now. I've dropped the attendance link.